I want the students to actually physically build this device and see that they can build a thing and hold it in their hands and make it work, because there's no greater feeling than that exactly for the students. So it's a thing that they may not be extremely familiar with, but it's something that I think should work in order to really get them excited, especially as this is kind of one of their later projects, and it's a little bit larger in scale. So I'll try and keep the video reasonably short to the essentials. I'll probably do some pausing here and there rather than doing edit jump cuts later, in order to just set up the wiring, and then you can pause and play and copy and do all those things. So anyway, the idea is you start by giving them the fundamental principles toward the end of class. As you've gone through whatever the theory sections and things are, this is where you start to help answer some of the questions that are likely to come up, and you're running this as the part of the activity that they're going to go home and work on and finish. And so it's not as simple as they just go copy code and paste it directly into their finished project, because at the end of the day they have to build the physical thing. So if they have to build the physical thing, cheating literally does them no good in this particular circumstance. And that's why I guess we're maybe less concerned about academic dishonesty, because either you built the thing or you didn't, right? If it turns out that you submit the same video as somebody else, that's a whole other matter. So without further ado, let's jump over into the incredible Volt, and that's what's going to be developed today. So the one that I actually really like as a reference for this is an Instructable on the social distance warner. So this is one that is, I think, a very helpful reference. This is one that they're going to come up with a lot of different examples of this. A lot of them are going to be using the Arduino Nano, because it speaks USB-C and has a couple other features. It's also pretty small and lightweight. It's maybe a little bit more power efficient than the Uno, but again, this one uses exactly the kinds of parts that are in their specific kits. And I'll see if I can get to a point where I can actually build all of these physical circuits. I'm just trying to get the concept training videos put together for the instructors first, then I will put together a couple videos later of the actual physical hardware working and show you any sticky points or where they will likely have failures with some of what they're trying to do. So let's get into this. Again, just like with about anything, we're going to need some kind of breadboard. We will need an Arduino. This is still going to be our power supply for this. I think in this example they run it off of battery power, if I remember right. Maybe they don't in the actual setup. The actual circuit itself, super duper simple, really quick to actually put together. A handful of LEDs, some resistors, a buzzer, and the ultrasonic sensor. So it doesn't look like much, but I'm going to switch back over to all of the components so that I can pull some of those out. We're going to need some resistors, so I'm just going to throw one out here. We don't need any diodes or anything super fancy in this case. The ultrasonic distance sensor, they have a couple different models here. So this one I think is actually, let me check the kits, because there's options for both the 3-pin and the 4-pin. So let me double check real quick, as a matter of fact, which ones we're actually using in the kits, and see which one we need to wire up, because that'll make a little bit of a difference. The 4-pin is the one that's used here in their example, and so that's probably what we're going to set the code up for. The 3-pin is going to wire up similarly, but it's only got a single signal pin. I believe all of the kits that we're using are going to run with the 4-pin. So for now, that's what I'll go ahead and set up in this guy. That should keep things still fairly well organized. So our sensor should be very much like this one, and we're going to set up our LEDs as well. So that will be down here with some of our indicators and lamps. So I'm going to set it up to be, yeah, I guess something like what they've got there is probably reasonable. We're going to do 2 red ones. I'll go ahead and move them up to give us just a little more room to work with. You want a couple different colors for this project, and what this will do is give them yellow or orange. Either of those is acceptable, and they should have a variety of different color LEDs. They should have a couple of each color. Doesn't matter whether they're large LEDs or small LEDs, depending on which specific kit they get, and if we have to make adjustments, we'll make those adjustments as we need to. So this, I'm going to go ahead and make one more of these. Need to move that one over, make a copy of that one. Okay, so we have our LEDs. Now we also need our resistors. Now I'm going to do something a little bit cheeky just because I am in the mood for it. It's been some kind of a week, so what I'm going to do is I'm going to strap all of my negatives to a single line, and I can do that because reasons. And by doing this, I'm going to drop all of my wires to ground on a single resistor because that works just as well. In principle, you have a little different resistance, but you're still protecting each one of the resistors. So I'm actually just doing this out of pure and simple laziness, but you can do a fancy, nicely wire routed setup just like they do here. It'll look a little cleaner if you spend a little bit more time. We're also going to need the buzzer. So not the vibration motor, but the piezoelectric speaker. So this is one that I think is one of my favorites, and I'll make sure that desktop audio is being captured here. And there's a lot of reasons why I like this particular one. I guess maybe I won't show that particular demo, but there's a couple reasons why I like it. So positive, negative, fairly self-explanatory. This one, we're going to bring the positive in from pin 3, I believe it is here. So pin 3, that's going to be, I'm going to leave that one as an orange signal pin. We're also going to wire in, for this one, ground. Again, fairly self-explanatory. I'm going to do a couple wire segments just because I think it looks slightly cleaner on this side of the board. Same thing for this. This one's going to be red, carrying our power in. So we need our ground, run from the board. This one will be black, and we're going to need our 5 volts. Okay, so we've got our 5 volts in, run to our sensor. So we need the trigger and the echo, 2 different signal paths. So for this one, I'm going to connect from the echo over to this one. Echo is connected to 6. So that one can be green, and that's actually fine. And this. Now, the buzzer tone, we'll go ahead and run this as intended, and then we'll see. So this as a starting point, let's walk through quickly kind of what this does so that I don't just gloss over it and leave anybody behind. So same sort of thing that we do for everything. We start by initializing. So we initialize what our variables are going to be. So we're giving these each a name and then telling it which pin it's going to go to. Then we tell the pin what its job is. So you name it and claim it. Then you set up the job that it's going to do. Is it going to be input or output? And so each of these names for the variables goes with input or output. The echo pin is the input. That's the thing we're reading in. Then we set up our loop that is our primary function. You can see here it's just a bunch of if-else logic. We'll kind of step through it a little bit so that you guys understand what it is in case the students are stuck on trying to figure out how to adapt whatever logic they have for that one or the other one. The pin definitions are really important because if they're using a tutorial for another type of Arduino, the pin assignments can be a little bit different in how they function. And this is where we're looking for information in. So first thing we do is we set up a couple variables. These are stored as long data types. These so duration and distance. Distance write or digital write is one of our key commands. We're either digital write or digital read on most things. So digital write, the trigger pin to low, so we switch it off. We delay a few microseconds and then we switch it on. So turn the trigger pin to high. Again, small delay, trigger pin to low. So the idea is this is setting up a loop, right? So what's it doing? And this sets up duration and distance. And so the duration divided by 2. This comes from a calibration variable, and this may or may not be accurate for the specific sensors that the students have. And part of this project is we want them to say, gee, is that right? I can measure this thing with my tape measure and this is 6 feet away, but the sensor, when I look at it, is telling me actually it's only 3 feet away. Well, obviously that's not right. So how do we recalibrate it? That's all set up here in the distance equation. So this is something that we'll have to play around with a little bit in order to get it to be just exactly right for the specific sensors that we have in the kits. Again, I don't have these values yet because I'm trying to develop the theory piece out ahead of actually putting together the physical hardware. But I'm really excited about this one because as much as I'm very much of the opinion that a lot of the nonsense we're doing is security theater for all of these things going on right now, this is actually a cool piece of technology that the students can build and use to actually really measure stuff. That's what I'm excited about for this project. So we set up the logic, a bunch of if-else cases, so they could do else-ifs here, but anyway. If the distance is less than this amount, then you set the sound to 250, 260, 270, depending on as the distance gets less and less and less, and they change from LED. So they write the LED to high. So if you're, in this case, they're doing LED. So we'll track this. So LED is pin 13. So starting from 13, so they start from green and go all the way up to red as things get closer, is the way this is set up. So LED 2, 3, that's all counting down. So 13, 12, 11, 10 is counting down. 2, 3, 4, 5, 6. Those are all counting down as the distance gets less. So less than 25, less than 20, less than 15, less than 10, less than 5. And so as this gets closer and closer and closer and closer, this scale will increase the frequency. That's what this is. And so we'll look at that as we go to do the simulation, and you should be able to hear it because I'm capturing the system sound. Then you set the light to low. If the distance is greater than 30, then you print out back to the computer out of range. No tone and buzzer. Now This one, there is a serial monitor, but I haven't played around with it too much, so we'll actually probably take a look and see how that works, or see how well the serial monitor works, because I don't think I've actually had to use that on many Tinkercad projects yet. So then you print out the distance, and so for this, we'll actually take a look at this. There are, I think, there's enough pins on here that you could also do this with an LCD display and do a readout, but that's a challenge objective that you can certainly set for students, especially if they feel like this is beneath them. As a project, the challenge objective for this one, a really good one frankly, is how to rearrange the pins so that you're taking so you're able to actually run an LCD display at the same time. It can be done. You have just exactly as many pins as you need. You might actually have one extra technically.